Good morning, dear students. My name is Ferhan Mazher, and today the subject we are studying is Physics 5054. This is Cambridge O Levels Physics, and today we have set our hearts to solve a paper 4. This paper is called Alternative to Practical. We also call it ATP. Today we have selected May-June 2011 4-1 paper. This paper 1 belongs from the zone 1 or the variant 1. In this video, you will find the solution of the ATP paper, this ATP paper. So my name is Ferhan Mazher. So let's start. So the paper is showing up on your screen, and let's start. The time allowed for this 4-1 paper is 1 hour. Okay. A student investigates the behavior of a capacitor as it is charged. The student connects a capacitor C and a resistor R in series with an ammeter and a DC power supply as shown in the figure 1.1. So you can see here we have the DC power supply, here we have an ammeter, this is a fixed resistor, and this is capacitor. The student notices that the reading on the ammeter decreases to 0. Explain why there is no current in the circuit after some time. You see in the start, these two plates, these are the plates of the capacitor, and gradually what will happen on these plates, the opposite charges will accumulate. So when you start this observation, there is no charge on these two plates. So the charge from this terminal of the battery and charge from this terminal of the battery, they will start accumulating on these two plates. So as the charge will build up on these two plates, the potential difference between these two plates will increase. At the start, the potential difference between these plates will be 0. And as the charge will accumulate on the opposite charge will accumulate on both the plates, the potential difference between these plates will increase. And after some time, when this is fully charged, this is positive, for example, to its maximum capacity, and it is negative to its maximum capacity, the potential difference between these two plates will become equals to the potential difference or the EMF of the battery. Then no more charge will come from the battery and accumulate here. So at that moment, the current flowing in the circuit, that will stop. So the ammeter will show 0 reading. So their question is explain why there is no current in the circuit after some time. So you see, when the capacitor is charged, is fully charged, the current stops flowing in the circuit and the ammeter shows 0 reading. So that's my description. Okay, so the capacitor becomes fully charged, so now no more charge flows in the circuit. So that is our answer. So you can see the marking scheme as well, that's showing up on your screen. Okay, the student disconnects the circuit using a movable lead as shown in the figure 1.2. In order to discharge the capacitor, the student may connect the end P of the movable lead to either the point X, Y, or Z. State and explain which connection will discharge the capacitor the fastest. So the charge can be discharged, the charge which is stored on the capacitor, it can be discharged if when you complete the path for the plate A and the plate for both the plates, if you complete the path and that path has the lowest resistance. So where the path will have the lowest resistance, so for example, if you connect here, then between this plate and this plate, the path will have ammeter and a variable resistor. So they will have resistance, so the flow of the current will obviously have opposition, so it will flow little, means the rate of flow of that charge will be less. But if you connect it at Z, this plate through this wire will be connected with the Z, so then you will have this plate, so there will be no resistance. So when there will be no resistance, then the flow of the charges will be a large amount of charge will flow in a very short time. So the capacitor will be discharged very quickly. So my guess is that connect the P at the point Z, then the resistance of this path will be very small. So this will happen very quickly. So here is my answer. Connect the P with the Z. There will be no resistance. So largest current will flow from one plate to the other plate of the capacitor. And the capacitor will very quickly discharge. Z and no resistor, capacitor short circuited, circuit current large. Okay, so our answer is right. Okay, so now we are going to the next part. That's the B part. He says the capacitor is now fully charged, fully discharged. The student reconnects the circuit of the figure 1.1 and observes the initial ammeter reading. The ammeter is shown in the figure 1.3. So what's the reading here? It's 80, it's 90. There are 5 small divisions. So each division is representing 2, so it is 88 milliampere. The question was state the reading on the ammeter, so that's 88 milliampere. So I think it's 88 milliampere. Okay. Now we are going to the next part. He says the student observes the needle as the current in the ammeter begins to fall and starts timing when the current is 80 milliampere. The time t for the current to fall from 80 milliampere to a value I is measured. Readings of current and the time t are shown in the figure. Okay. So when the current is 80 milliampere, they started their observation and the time is 0. And when it becomes 60, it is 6.33 seconds. When 40, it is 15.25 seconds. When the current is 30 milliampere, the time has passed how much? 21.58 seconds. And when the current is 20 milliampere, the time has passed is 30.50. So when the time has passed 10 seconds, the current is 10 milliampere, the time is 45.75 seconds. When the current is 5 milliampere, the time passed is 61 seconds. Okay. So now they want us on the figure 1.5, which is this figure 1.5, which is, let me show you the whole thing. Okay, so this is that graph. It's a 4-mark question. He says on the figure 1.5, plot the graph of I in milliamperes on the y-axis against the t in seconds on the x-axis. Draw the curved line of the best fit. Okay, so we have to draw the graph, and I will take the t on the x-axis. The t will be on the x-axis. The t is supposed to be on the x-axis. So here you see the t value is going from, let's say, from the other. Let me reduce the size. So the t is going from, this is that table, from 0 to 61. So you can see here 10, 20, 30, 40, 50, 60, 70. And that is on the x-axis. And the I value is going from 5 to 80. So 0, 10, 20, 30, 40, 50, 60, 70, 80, and 90. Okay. At 0, you have 80. At 0, we will have 80. This is the point. Okay. And then at 6.33, it is 60. 6.33 will be here. Here somewhere. Yeah. And it is, I think, how much? 60 at 15.25. At 15.25, this is the point. And how much is that? At 15.25, you will have 40. So I will put this dot. And at 21.58, you will have 30. At 21.5, you will have 30. Put this dot. And at 30.5, you will have 20. At 30.5, you will have 20. Put this dot, okay? So at 45.75, approximately 46, you will have 10. This is here, 10, okay? So at 61, you will have 5, okay? At 61, we will have 5. So this is the dot. So then after putting the dots and labeling the axis, you will have to draw the curved line of the best fit. So I will try to, this is my best fit line. So let me show you. Okay, so I try to draw a line of best fit. This is the curve of best fit. Okay, so this is that. Just ignore these dots. Okay, so this is that line of best fit. Okay, now what they want us to do. Use your graph to describe the relationship between I and T. Okay. So when the I is 10, you see the T value is, I think, 51. And when it becomes 20, this is 30 something. Okay. So as the T increases, the value of the I decreases non-uniformly. You see, one very important thing is that I have not used the word direct inversely proportional. Instead of saying inversely proportional, I am saying as the T increases, the value of the I decreases non-uniformly. I'm not using the word inversely proportional. The reason is when I doubled the time, uh, the I value has not become half. So if I double from 10, if from 10 seconds, if I take the time to 20 seconds, the time has become double. If the current will become half, then I will say the word inversely proportional. Otherwise, no. Then I will simply say, okay, as T increases, the value of I decreases non-uniformly. I hope you understand. So this is the marking scheme. You can look at the marking scheme carefully. You can pause the video. Then it says the resistance R is 100 ohm. Use your graph to find the potential difference V across the resistor at the time T is equals to 40 seconds. You may use the relationship V is equals to IR. Okay. So from the graph, when the time is 40, okay. So from this graph, when the time is 40, I will check how much is this current. This is 11, 12, 13 ampere. So I know the resistance, that's 100 ohm. That's 100 ohm. And I know the current, that's 13 milliampere. So I can find out the potential difference. You know, I from the graph is 13 milliampere. So according to the Ohm's law, V equals to IR. So V, I want to find out the I value is 13 expo minus 3 because in this formula, we take the value in amperes, not in milliamperes. The resistance is 100 ohm. So 13 expo minus 3 multiply 100. So it will be 1.3 volt. So the voltage drop will be 1.3 volt. So let's check here. So our answer is right. You can see here. Okay, so now we are on the next question. The next question is question number 2. He says a displacement can is a container with a spout used to determine the volume of an object. Figure 2.1 shows a displacement can and a cross-section of the can. So this is your displacement can, and this is the spout. So the water is filled up to the level of the spout. And the can is filled with water to the level of its spout. Explain how the displacement can is used to measure the volume of an irregular object, such as a glass stopper. State any additional apparatus that is required. So the method is very simple. So we will take a measuring cylinder, a dry measuring cylinder, and we will place that dry measuring cylinder here under the spout. So then I will take that glass stopper and I will gently, very gently place that glass stopper in this displacement can. So when you put the glass stopper here, the level of the water obviously will go up. So through that spout, the water will be displaced and it will be collected in the measuring cylinder. So when you have placed the glass stopper in the displacement can and the water will displace, and when the water stops dripping from the from the spout into the measuring cylinder, then check how much is the volume of the water which is collected in the measuring cylinder. And whatever will be the volume of the water which is collected in the measuring cylinder, that will be the volume of that irregular object or the glass stopper. So it's a 3 marks question. Let me show you my written answer. Okay, so my answer is showing up on your screen and hopefully you can see that. That's the question number 1. 2 is A part, is first portion. Put a measuring cylinder under spout. Put glass stopper in displacement can. Water displaced will be collected through spout into the measuring cylinder. Volume of this water will be volume of the glass stopper. It's a 3-mark question. So you can see the marking scheme of the first A, question number 2A, first part. So you can pause the video, you can take your time. Our answer is right. State one possible difficulty in measuring a can that has a very small diameter. So if your displacement can has a very small opening at the top or very small diameter, this diameter, so maybe it's not possible for the glass stopper to fit into the displacement can. So we will not be able to put the the glass stopper into the glass stopper might not fit in the displacement can. Okay, so our answer. The second part is a spout that is attached near the bottom of the can. So you see this spout is attached here at the almost at the top. If this spout is here, then the level of the water which you can keep in this displacement can will be only here. So that when you put the glass stopper, so the glass stopper will might not be fully immersed in the water. Level of the water will be low, glass stopper might not be fully submerged or immersed. So this is the answer. So our answer is right. Then they said describe 2 precautions that will make the results more accurate. So you see, whenever you use the measuring cylinder, the measuring cylinder must be dry and it should be clean and dry. No water from the spout should be dripped out of the measuring cylinder. And when you put the glass stopper into the displacement can, you should do it very gently and slowly so that the water do not splash and the water should not spill out. These are the precautions. When measuring volume of water in measuring cylinder, it should be on a table, not in your hand. Okay, so whenever you read from the measuring cylinder how much is the volume of the water in it, it should be placed on a horizontal table and the level of the water should become steady and then you should read it. Measuring cylinder must be dry before using it. Okay, so these are 2 precautions which I have written. So question number 2A, third part, you can see there are a lot of avoid parallax error, repeat and average, use level bench, measuring cylinder dry before use, stopper dry before immersing. Yeah, that's very important. The stopper also must be dry before you put it into the displacement can. So use sensitive measuring cylinder. Okay, so these are some precautions. To determine the density of the glass, an additional quantity must be measured. State. You see, whenever you calculate the density, density is mass divided by volume. So with the help of the measuring cylinder and the displacement can, you can find the volume. Now I also need the mass of that glass topper. So the quantity which need to be measured is the mass of the glass topper. And the instrument which we can use is an electronic balance, span balance, whatever you like to write. So I've written mass is the quantity which we need to measure, and the electronic balance can be used. So you see, okay, a student investigates, that's the question number 3 of this paper. A student investigates the frictional force on a block of wood sliding along a bench. The block of wood has sides of length 15 centimeter by 10 centimeter by 5 centimeter and has a hook attached as shown in the figure 3.1. Figure 3.2 is a list of apparatus available to the students. Block of wood with hook, Newton meters with different ranges, 1 Newton, 0.5 Newton, 0.1 Newton weights and hangers, thin string, pulley, stands, clamps, and bosses. Okay. So their question is, okay. The student measures the force needed to make the block of wood just start moving along the bench. Choosing apparatus from the figure 3.2, describe a procedure that the student can use. Okay, so I think that I can use a string. I will attach the string here, then I will attach here a Newton meter. Then I will attach the string and that Newton meter, the string with that Newton meter. I will put a pulley here through that, over that pulley, it will go down. And here I will put a hook, and on that hook, I will put mass, load, weights. So I will, first of all, I will, for example, use a 1 Newton weight, and I will observe what is the reading on the Newton meter. This wooden block, for example, do not slide. Then I will put another weight on this hook, and another weight, and another weight. And I will keep noting what is the reading on the Newton meter. So gradually reduce the new weight which you are adding up. So at the start, you can put larger weights, but as you have put 1 Newton, 2 Newton, 3 Newton, for example, and then you are supposed to put smaller weights. So we are looking for a point, the maximum reading on the Newton meter before this wooden block starts sliding. So keep adding smaller weights, more and more smaller weights, and keep noting down what is the reading on the Newton meter until this wooden block starts moving to the right. So the maximum reading which you will note on the Newton meter before the block starts sliding, that is the force which is needed to slide this wooden block on that table. So this is I hope you understand this description. So here I have tried to make that diagram. So this is that wooden block. So with the help of the string, I have connected here this Newton meter, and that string is passing on a pulley. And then I have put a hook here, and you can see I have added weights here. So that is how you will do this. So this is my written answer. It's a 2 marks question. So here is the block, here are the strings, the Newton meter over the pulley, the string passes, then here we have the weights. Connect the wooden block, a Newton meter, and weight with help of a string as shown in the figure. Use pulley on edge of table. Increase the weight hanging by the string. Note the maximum force shown on Newton meter before the wooden block starts sliding. It's a 2 marks question. Hopefully you understand. And here comes my answer. So, okay. So this is the marking scheme. You can pause the video. Describe one way to make the experiment more accurate. So repeat the experiment 3 times and take average value of the force. And I have written given this answer, you can increase the force slowly, add smaller weights. Don't put very large weights. Okay. Increase the weight slowly. I mean, put smaller weights. Smaller weights for example, instead of putting 1 Newton, 1 Newton, 1 Newton weights, put 0.1 Newton, 0.1 Newton, 0.1. Put smaller weights. Increase that force slowly. And the student now repeats the experiment, varying the surface area of the block of the wood in contact with the bench. Straight how the student does this or with the same block of the wood. You see the face of the block which is touching, this larger face is touching. Now you can put this face in contact with the table, so the surface area will change. Okay, just change the side of the block. Use different side or face of the block to be in contact with the table. That's my wording. Use different side of the same block. Okay, so that will change the surface area in contact with the table. A teacher suggests that the frictional force F is related to the weight of the block by the equation F is equals to Kw, where K is a constant. The student varies W by placing additional weights on top of the block and measure F. On the figure 3.3, write the headings in the table used to record the results. So F will come here, and here I will put the weight, W. W will be measured in newtons and F will be also measured in newtons. So weight, newtons, force in newtons. This is the answer. Explain how the student can obtain the value of the K using a graph of the results. You see, for example, on a certain value of the W, you will get a certain value of the F. On a certain value of another value of the W, you will get another value of the F. So take the W on the x-axis and the F on the y-axis, then plot these points, which you will have in this figure 3.3. And then you will join those points on the graph, and that will give you what I hope straight line. And then find the gradient of that graph. So the gradient of that graph will be equal to the K. Calculate the gradient of the graph between F and W. Gradient of the graph is equal to the K. So what they say, plot F against W or W against F. Find gradient of the graph. So the gradient of the graph will be K, or the gradient of the graph will be 1 by K. You see, try to understand this point. If the W here, the K will be F by W. So this F must be on the y-axis. If you take the F on the y-axis and W on the x-axis, then the gradient of that graph will be equal to the K. But if you take the W on the y-axis and the F on the x-axis, then the gradient of that graph will be equal to 1 by K, because the K is F by W. So keep the F on the y-axis and W in the x-axis, then the gradient of that graph will be equal to K. Simple, I hope you understand. A student walk away from a street lamp at night and notices that his shadow changes. The student investigates shadows in a darkened laboratory. He uses a lamp on a stand and a vertical card as shown in the figure 4.1. So here we have a card and here we have a stand. On that stand, I have this lamp. So due to this light, the shadow of this card will be here on the bench. On the figure 4.1, draw a ray of light from the lamp to the bench just passing over the top of the card. So I will join this and the top of this card with the bench with a straight line. Okay, very simple. You can see here I have drawn that line. You can see that line. So that was the 1 mark question. Then there's the region of the bench that does not receive light from the lamp is the shadow of the card. On the figure 4.1, draw a line on the surface of the bench to indicate this shadow. So this is the shadow. You see, this is the shadow. Then the question is, the card is moved along the bench away from the lamp. State what happens to the shadow of the light. Okay. So it's a very tricky thing. If this point is here and you join this, so what will happen? That's the question. You can do it actually. Move this here or here, let's say. Same height. So what will happen with the shadow? The shadow of the card will become longer. Okay? The shadow of the card will become longer. You can do it actually. Just make the same height here. Okay? Join again and check that if the new shadow is longer than this previous shadow. Okay? The C part is, he says, the shadow of the card produced in the laboratory is much darker than the shadow of the student in the street. You see, in the laboratory, it's a controlled environment and you have switched off all the lights, only the lamp on the stand that's lit. But in the street, you see, there will be many other sources of the light other than your own lamp. There might be street light, there might be traffic. So there are multiple sources of the light. So that's why the shadow in the street will be not that darker because there are multiple sources of the light. So in the street, there are more than one source of light. For example, street lights, moon, headlights of cars passing by. So that's the answer from the question number 4. So you can see that answer. You can pause the video with this question. So my dear students, today we have completed May-June 2011 Physics 5054 41 ATP paper. This is alternative to practical. This paper 4 was from the zone 1 or the variant 1. I have tried my best to explain you the concepts of this paper. I hope you will understand this. If you find this video useful, interesting, and it has helped you, please like this video. Also, don't hesitate to comment and share the link of this video onto your Facebook accounts, onto your Twitter account, and onto your Instagram, because that helps me to promote my channel. I think that it's a great blessing for me that I can make these videos and I can touch the lives of so many students around the globe. My name is Ferhan Mazher. Thank you very much. Have a good day. God bless you all.